Okay, folks, continuing along with Module 10, Learning Goal 10.3, know the Frank-Condon principle. Some of you might have some familiarity with this from instrumental analysis. So we'll go ahead and, like we always do, add our Chem touch to something that you may have already talked about in your other classes. So the Frank-Condon principle starts under the Born-Oppenheimer approximation, which says that we suppose the nuclei are so much heavier than an electron that they may be treated as stationary while electrons orbit in their respective fields. So we talked about this before when we built up our model of the hydrogen atom. And now we can see another application of this is related to the Frank-Condon principle. So again, the nuclei being so much heavier than an electron move relatively slow and may be treated as stationary. So if we think about like a simple molecule right here in the ground state, and I'll denote that with X, before, and let's suppose this molecule now undergoes an electronic excitation. So it moves up to some excited state, okay? And I'll just represent that with this picture here, and suppose we go up to the A state. So because this electronic transition occurs so quickly, the nuclei will not approximately move over that period of time. So Frank-Condon says the molecule will undergo a transition to the upper vibrational state that most closely resembles the wave function of the vibrational ground state of the lower electronic state. So in other words, we can see in this picture right here, this is our Frank-Condon, or our vertical transition is what this is often referred to as, the vertical transition. So our state just goes up vertically and will hit the point in the excited state that's directly above it. And because these nuclei are moving so much slower than that transition takes place, we can see that we will access some not only electronically excited state, but some vibrationally excited state as well. So we will hit the turning points of whatever vibration overlaps with that. So if we look at that in more detail, and remembering in the simple harmonic oscillator model, we have this potential energy well, and our ground vibrational state was this simple looking Gaussian, right? And if you recall, our next level looked something like this, where we had two of these humps, and here I'm showing you psi squared. And then the next one looks like the following, where now at the turning points there was more intensity. I'm kind of drawing this exaggerated. And then in the middle there was less intensity. So now, as we might imagine in this picture, depending on where we overlap in the electronic state and the ground state, we will hit that vibrational state that is directly underneath, because at the turning point, that wave function is really representative of the wave function in the ground state. Okay? And oftentimes we see electronically excited states being shifted out to larger internuclear separations because they typically have more anti-bonding character. So I'm going to write that down. More anti-bonding character typically, which means they are further separated from each other. So now when we think about how this relates to an absorption spectra relates that overlap. So for example, in this picture right here, we can see the vertical transition from the nu is equal to 0 state within the X ground state going up to the A excited state. And if I look closely, we can see that's overlapping with maybe nu is equal to 3 or so. And that will owe to the lambda max. So lambda max occurs where there is this strongest Frank-Condon overlap. And then as we scan in energies, right, in the spectrum, I know it's like tilted on its side, right? But as we scan either away from that lambda max, either to smaller wavelengths or larger wavelengths, we have less overlap, so we have a less intense spectrum. And additionally, if we have very well-resolved vibrational features, we will see those in the UV-Vis spectrum. So typically, like if we see a UV-Vis spectra that has all of these like interesting looking features, those are the vibrational states within the excited electronic state. And so that's intensity versus wavelength. However, if we see a UV-Vis spectrum that's, rather simple looking, perhaps just one peak, then we're likely not overlapping with the vibrational states, or our vibrational states are so packed together that we don't have the resolution to see that, and thus we get this Gaussian, where as we fall off to one side or the other from lambda max, we have less overlap than compared to that vertical transition. Okay, so that was just a brief description of Frank-Condon. We'll explore this in more detail in the next video.